Linearity of expectation. For any real number c, we can define the random variable cx by setting c times x of u equals to c of x of u for all u in omega. The following innocent-looking theorem proves to be extremely useful in enumerative combinatorics. Theorem 15.18. 1. Let x and y be two random variables defined over the same space omega. Then the expectations of x plus y is equals to the expectations of x plus the expectations of y. 2. Let x be a random variable and let c be a real number. Then the expectations of c times x is equals to c times the expectations of x. So taking expectations is a linear operator. The best feature of this theorem is that it does not require that x and y be independent, no matter how deeply x and y are intertwined, nor how hard it is to compute, say, the probability that x is equals to y. The expected values of x plus y is always given by this simple formula. This is why linearity is the most useful property of expectation and is applied to a very wide array of problems. Proof of theorem 15.18. 1. Let x1, x2, x3, and so on until xn be the values that x takes with a positive probability, and let y1, y2, y3 until yn be the values that y takes with a positive probability. Then the expected values of x plus y is equals to doubling summation with outer summation summing with index I starting from 1 to n, and the inner summation summing with index j starting from 1 to m, with inner terms xi plus yj times the probability such that x is equals to xi and y is equals to yj, which is equals to doubling summation summing with index I starting from 1 to n, and the inner summation summing with index j starting from 1 to m, with xi times the probability of x equals to xi, y equals to yj, plus, if we replace xi with yj for the same doubling summation, times with the probability of x equals to xi and y equals to yj, which is equals to the summations. If we separate the summations, that is, the first summation is summing for all xi times the probability of x equals to xi, summing with index I starting from 1 to n, plus the summations of yj times the probability of y equals to yj, summing with index j starting from 1 to m, which is equals to the expectations of x plus the expectations of y. 2. Let R is in omega. Then, by definition, Cx of R is equals to C times X of R. So if x1, x2, x3 until xn is the range of x, then the probability of Cx equals to Cxi is equals to the probability of x equals to xi. Therefore, the expectations of C times x is equals to the summations of C times xi times the probability of Cx equals to Cxi, summing with index I starting from 1 to n, which is equals to C times the summations of xi times the probability of x equals to xi, summing with index I starting from 1 to n, which is equals to C times the expectations of x. In order to be able to better appreciate the surprising strength of the theorem 15.18, let P equals to P1, P2, P3 until Pn be an n permutation. And let us say that I is a value of Pi is smaller than both of its neighbors. That is, Pi is less than Pi minus 1 and Pi is less than Pi plus 1. We require 2, which is less than equals to I, which is less than equals to n minus 1, for I to be a value. Theorem 15.19. Let n, which is greater than equals to 2, be a positive integer. Then, on average, a randomly selected permutation of length n has n minus 2 over 3 values. Without theorem 15.18, this would be a painful task. We would have to compute the number v of j of n permutations with j values for each j, a difficult task. Then we would have to compute the summations of j times v of j divided by n factorial. Theorem 15.18, however, turns the proof into a breeze. Proof of theorem 15.19. Take n minus 2 different probability variables y2, y3, y4, and so on till yn minus 1, defined on the set of all n permutations as follows. For an n permutation p, let yi of p equals to 1 if I is a valley, and let yi of p equals to 0 otherwise. Then for 2 which is less than equals to I which is less than equals to n minus 1, every pi has a 1/3 chance to be the smallest of the set pi minus 1, pi plus 1. Therefore, the expectations of yi is equals to 1/3 times 1 plus 2/3 times 0, which is equals to 1/3. Define y equals to y2 plus y3 plus y4 and so on plus yn minus 1. Then y of p is the number of values of p. Therefore, theorem 15.18 implies that the expectations of y is equals to the summations of expectations of yi, summing with index I equals to 2 to n minus 1, which is equals to n minus 2 times the expectations of y1, which is equals to n minus 2 divided by 3. Variables similar to yi, that is, variables that take value 1 if a certain event occurs, and the value 0 otherwise, are called indicator variables. Theorem 15.20. The expected value of the number of fixed points in a randomly selected n permutation is 1. Proof. We define n different probability variables, x1, x2, x3, and so on to xn, on the set of all n permutations as follows. For an n permutation p, let xi of p equals to 1 if pi equals to I, that is when p has a fixed point at position I, and let xi of p equals to 0 otherwise. As pi is equally likely to take any value j in n braces, it has a 1/n chance to be equal to I. Therefore, the expected value of xi is equals to 1/n times 1 plus n minus 1/n times 0, which is equals to 1/n, for all I in n braces. Now let x equals to x1 plus x2 plus x3 and so on plus xn. Then x of p is precisely the number of fixed points of p. On the other hand, applying theorem 15.18, we get the expected value of x is equals to the summations of expected values of xi, summing with index I starting from 1 to n, which is equals to n times the expected values of x1, which is equals to n times 1/n, which is equals to 1, and which was to be proved.